All right, hello. We are going over the second Mullins SI worksheet. I apologize for the kind of annoying tapping noise that my Apple Pencil makes. I was rewatching the recording and it was really annoying. Hopefully it's not too bad. All right, let's go over this. So for these resonance structure pairs, we have a few rules for how we're going to determine if it's more contributing. The first one that we want to make sure we are fulfilling the octet rule. That's the most important rule. We want to make sure everything has an octet. Minimizing formal charge is also good. So minimize charge. We also want to maximize the number of covalent bonds. Furthermore, if we cannot minimize charge, we want the negative charge on more electronegative atoms. That kind of makes sense, right? Electronegative atoms, they want electrons, and therefore the negative charge will be more stable on them. So we can go ahead and use these rules to solve this first problem. So it gives us these two resonance structures here. The only difference between these two is that for this, we have carbon with a negative charge, and then we have oxygen with a negative charge. And in this case, of course, everything has an octet here. We've minimized charge as much as we can. Number of covalent bonds is the same. So basically, what this comes down to is oxygen is more electronegative. So O is more electronegative. Therefore, this one is more contributing. This one on the right, we just talked about how we want negative charges on more electronegative atoms, and we want positive charges on less electronegative atoms. Here, though, like we said, the octet rule is the king. Here we have six electrons. Here we have 8 electrons. So this right structure is going to be more contributing because it fulfills the octet rule. All right. Number 2, we're drawing the Lewis structure for PO43-. That's the phosphate ion. And then we have to draw 3 other resonance structures. So let's start out. Hopefully this is kind of second nature by now, but let's start out with our process so we can count the number of valence electrons. Here we have 5 from phosphorus, 6 times 4, and then plus 3. What this ends up being is 8 plus 24, which is 32. If we were going to draw 32 valence electrons, that would look something like this. To confirm that we are correct, we want to go ahead and draw formal charges at this point. And of course, right, phosphorus can break the octet rule. We have a negative charge right next to a positive charge. Negatives attack positive, so we can draw a structure where instead we draw a double bond between one of the oxygens. Now, the reason why I showed it this way initially was because really we could have chosen any of these oxygen atoms to attack that phosphorus bond, right? Therefore, it stands that we can, instead of just drawing this double bond for future resonance structures, we can also draw double bonds with any of these oxygens, right? If we want to show the arrow pushing mechanism for these resonance structures, we can do something like this, where we can just draw all of the possible different double bonds here. Likewise, we can just do the same thing with this bottom one, push the electrons up. And once again, we can do it down here as well. And this ends up giving us all of the possible resonance structures for phosphates. And I'll go ahead and draw brackets around them, because we draw brackets to imply that the real structure of phosphate is a mixture of all of these different contributing resonance structures. So we can draw it like this. Part B says that the PO single bond is usually 1.53 angstroms and the double bond is 1.4 angstroms. And we have to explain why the PO bonds in the phosphate ion is actually slightly lower than the single bond length. So we see in this resonance structure, we have basically all of these oxygens have mostly single bond characters. So like picking on this oxygen right here, we'll call this oxygen 1. It has a single bond in this resonance structure. It has a double bond here, a single bond here, and then a single bond here. So really 3/4 of its character is from a single bond, which explains why the bond length is mostly close to this 1.53 angstroms, but it's slightly shorter, meaning that it has some double bond character. Right, so we can say for this answer, we can say resonance gives each oxygen some double bond character, which shortens the bond. Cool. All right. Now we are given this structure to the right, and we have to respond to the following prompts. So what is the hybridization on carbon 1? For this class now, we used to ask simply what are the number of areas of electron density. Now we learn that we need to draw, we need to learn if there's resonance structures possible. So if there's resonance possible, we need to account for that in our hybridization. In this case, there's no other kind of pushable pairs on this carbon 1, right? So this carbon 1 right here, we have a single bond and we have the double bond and we have this hydrogen here. But there's no other resonance structures we can kind of draw. So basically, we're just going to conclude we have 1, 2, and then 3 areas of electron density. So 3 areas of electron density, that's an sp2 hybridized carbon. All right, the hybridization on nitrogen, we're going to ask the same question. So how many areas of electron density do we have? We see we have 1, 2, 3 for this bond here, and then we have 4. We have this lone pair. So we have 4 areas of electron density. However, we need to ask ourselves, is resonance possible, right? And you see here, right, we have a pushable pair. We can push this pushable pair onto this carbon. And you may say, well, this carbon, it already has an octet. How can we do that? Well, it has a pi bond here that we can push, right? So if we were to draw this structure, it would look something like this. And of course, this isn't super stable. However, it is a resonance structure. And therefore, now we can take a real look. 1, 2, 3 areas of electron density, right? So 3 areas of electron density with resonance. Therefore, it's sp2. This is a hard problem. One people often miss on the first exam. So just be prepared. You need to train yourself out of the Gen Chem mindset and look for resonance structures instead. What is the shape of the nitrogen? Well, we just drew these resonance structures. It's sp2. That means it's trigonal planar. This question below, D, it's asking us what's the bond angle between, so if we take a look at this molecule, it's asking us what the bond angle is between these carbons and these nitrogens, right? So this carbon right here, the middle carbon, is an sp2 hybridized carbon, and therefore it's trigonal planar. So the bond length, or the bond angle between these is going to be 120. So we have this, that's 120 degrees. Draw 3 possible resonance structures. So we can do that. We've already drawn one. This asks us basically to draw 3 more. We've already drawn one. So we can use this structure that we have down here. We can use this as a kind of guideline for where to go next. Here we have, clearly, this carbon's negative. We don't really like negative carbons. And we have a pushable pair right here. This carbon next to it, it doesn't appear to have a place. It doesn't appear to be a place that we can push. However, we can just take these electrons from the pi bond and put them on that carbon. So we can't do that. I'll change colors. So we can push these electrons like this. To get this negative charge on that carbon. And then we can do the exact same thing here, where we basically just shift this lone pair onto a different carbon. Like that. So these are 3 possible resonance structures for that original structure here. It's kind of a little messy. Hopefully you can see that. All right. So just C to the right. What does the actual structure look like? This is almost a guaranteed exam 1 question where you have to recognize it's a weighted average of the resonance structures. So it's a weighted average of the resonance structure. That will always be the answer to this actual structure question. Below are the molecules methylformamide and then methylamine. Which molecule, so it's asking which molecule has a shorter C to N bond length. This worksheet is on resonance, but I imagine on an exam, when you're not thinking about resonance, it would be a little hard to answer this question. However, we can clearly see a difference here between these 2 molecules, right? Here we can draw a resonance structure where we push these electrons down, push those electrons up. Like this. Can we do this for methylamine? To determine that, we have to ask ourselves, is this carbon right here a place where we can push electrons? And in fact, it is not. If we decided to do that, we would end up getting this terrible structure, which you may wonder why that's terrible. It's because this carbon right here has more than an octet of electrons. It had 10 electrons. So which molecule has the shorter C to N bond length? It's the left molecule. Because resonance gives the C to N bond partial double character. All right, can the C to N bonds rotate freely? This is a tough question. I don't think we talked about this in lecture quite yet. But to determine if they can rotate freely, essentially what this relies on is, once again, we're going to have to use our resonance structures here. So you may recall from Gen Chem that double bonds cannot rotate. So single bonds can rotate. Double bonds cannot rotate. So double bonds cannot rotate. Therefore, the left structure, no rotation is possible because this bond has partial double bond character, right? So because double bonds can't rotate, that has to do with the fact that the p orbitals have to be overlapping. You can kind of draw a molecular orbital picture to help you out there. But the p orbitals have to be overlapping for this pi bond to form. And if the p orbitals are not in the same orientation, they're not going to overlap. Basically, if you try to rotate it, the p orbitals will no longer be aligned, and therefore that would break the double bond, which is not favorable. On the right, though, once again, we don't have that problem. We don't have resonance, and therefore we can do rotation since this is just a single bond, right? All right, thanks for watching. Keep doing the hard work. Do a little bit every day. Thank you for watching.